Let's begin, as we always do, in Chile. What's going on down in Chile these days? Well, Redbanc operates an ATM network there. And, as you can see from the link here, we have un artículo con muchas palabras en español. And the end result of all that is an employee was contacted for an interview via LinkedIn and was asked to complete an online application by running application pdf.exe like one does. And for some reason, things seemed to get out of hand and there were problems. If you would like it in English, then you can get it here. It's an article about hackers infiltrating Chile's ATM network after a job interview. Okay, so that's all we got on your threat for today. A question we should maybe ask ourselves is, do we need to write secure code? Is that a thing we need to do? A process we might use could be the following. Step 1, write some code. You all are super good at that. You're Tennessee Tech students. You're going to write some code, no problem. Step 2, fix security holes when they're found. Okay, fine. And then repeat, because it's always repeat. And the question I have for you is, what's wrong with this? Isn't this how we do it now? Is something wrong with this? Seems like that's a pretty reasonable approach. Well, suppose you want to sell software to another company or to other organizations, or you want to use it for something super important. Maybe you should revise that process. So here's an example. D-Link agrees to make security enhancements to settle Federal Trade Commission litigation. So what happened? Well, just prior to COVID descending on the world, the Federal Trade Commission sued D-Link for producing insecure products. That's right. They got sued for producing insecure products. Wow. So that's a thing you can be sued for? You can be sued if you have made a false promise. And what happened was, as you can see from the red box there, D-Link promoted the security of its products by claiming it offered advanced network security. But in fact, D-Link failed to perform basic secure software development, including like testing and remediation and preventable security flaws and so on. That's according to their complaint. So some of these included things like hard-coded login credentials on the D-Link camera software, easily guessed, username and password guessed, and storing mobile app login credentials in the clear and readable text on a user's mobile device. Jeez. So maybe what we're learning from this is, don't promise security. Right? They can't come after you. Like, I said, use at your own risk. That's what I said. I never promised anyone anything. And then you should be fine, right? So, from data from The Economist, in 2019, the year this happened, the software industry contributed $1.9 trillion to the U.S. GDP. That includes $845 billion directly. In other words, software sales account for that $845 billion. All the knock-on effects, all the things that are part of that whole industry, other things that are produced around that account for another account for the rest of that $1.9 trillion. That's a lot. U.S. GDP was $21.4 trillion in 2019, and so that's a lot. That's 8.9%, nearly 9% of the entire U.S. GDP. Wow, if it's that much money, then there may be folks who want to sue to try to get some of that money. So we could do a search, and in fact, I have conveniently linked the search right here for you to look for tort liability for insecure software. What's a tort? Well, we have two kinds of law in the U.S. We have criminal law, where they can send you to prison, and we have tort law, where we can fine you or do those sorts of things. Tort law governs you selling someone something else. Criminal law concerns you like punching someone in the face. And tort liability for insecure software, if you do that search, you may find some interesting results. Companies are already being sued and are already losing, and the insurance companies that those companies have really prefer not to cover losses if they don't have to. And so they can come back to the company and say, you got to pay us more unless you can show us that you're doing responsible development. Another thing that might motivate you is, occasionally some of us think about our fellow human beings and maybe worry about them a bit. The whole am I my brother's keeper thing. The modern world is software determined. That means capabilities of devices like your car, airplanes, everything is determined to a large extent by software. There are 16 critical infrastructure sectors. They're listed at the bottom there: chemical, financial, commercial facilities, food and agriculture, communications, government facilities, critical manufacturing, healthcare, dams, IT, the Defense Industrial Base, DIB, nuclear, emergency services, transportation, energy, and water. Those are all critical sectors. And these are industry sectors whose assets, systems, and networks are considered so vital to the U.S. that damaging them could have a debilitating effect on health or safety or security of the nation. Okay? Do those things involve software? If you have a company that writes software, would you like to peddle your software in one of those areas? Do you think your software might be used in one of those areas? So you might be a little more concerned. That covers most of what you'd want to sell your software to. Unless you're doing gaming, maybe. But even then, you might find yourself, gamifying something on behalf of the Department of Defense. It could come up. So that takes us to part 2. If you were sufficiently motivated to think, maybe I should try to write secure code, the question becomes, okay, how do you write secure code? Well, I should caveat this a little bit before we get into it. We're pretty deep into a class, like halfway through a class on secure software development, and we're just now talking about how do you write secure code. And that's fine, because this is not an undergraduate class where we're teaching you to write code. You've already had undergraduate classes where hopefully you learn some of these techniques. This is a graduate class where we're trying to get you to think about the issues and concerns and the challenges associated with this. In particular, my job is to get you to think with a security mindset. Okay, so let's think about how you might write secure code. What should we do? Well, one thing we could do is just learn all the CWEs, right? Put them all in your brain. Memorize them. You memorized the first million digits of pi. Who hasn't? Memorized a few thousand CWEs. Oh, there are too many? Oh, boo-hoo. So let's develop an automated checker that checks all the CWEs. Oh, wait, some of them can't be checked easily, and maybe they can only be checked on the source code, but some can only be checked on the binaries. Everything's complicated. And we still have the composition problem with other libraries. So maybe that's not going to solve our problem. It might help, but it won't solve our problem. So our earlier process didn't work. Write code, fix problems when they're reported. Maybe we can somehow change that process, and we might do it like this. Take reasonable steps to write secure code, and then fix problems when they're reported. You're always going to have step 2. I'm going to argue that that's going to eternally be there, because I'm going to argue that perfect security is impossible. So now we have some interesting words. We have reasonable steps and secure code. What do those things mean? Well, those just raise further questions. Do we have to protect a desktop solitaire application written in Node.js from state-sponsored hackers? Hopefully not, because that's kind of pathological, right? But we need to understand what's going on. If that desktop solitaire application in Node.js can be subverted by nation-state hackers, and they can use that to gain a foothold on a machine that then lets them do other nefarious stuff, then maybe the answer is yes, right? Remember back when we were talking about how security was binary? Well, that's kind of disturbing. So how do we have to think about what we mean when we say reasonable steps and secure code? So we're going to defer this, right? Because we have no idea how to define this in a nice, succinct, actionable way. We might say the following: secure code is code that is free from known weaknesses, but that's problematic too. The list of known weaknesses is always changing. It's very long, and we don't yet have super powerful auditing tools that will help us through this. They may be on the way, we're just not fully here yet. So the above definition feels like something actionable, right? Secure code is code free from known weaknesses, but that just pushes the problem over into the known weaknesses side and being able to verify that you're free of known weaknesses, and that just moves it around and it's hard. What about reasonable steps? Well, we can do better here. So we can try to distill what we knew about these various weaknesses, right? We try to collect weaknesses up and say, all the weaknesses that are in this pile are really symptoms of thinking this way about code, and if you think this different way, you won't make those mistakes. So we can try to turn that into specific guidance for how to write code in different languages, right? And it depends on the language. Remember, Lisp versus everybody else on integer overflow? So I have to think about things differently, right? If I'm writing code in standard ML, or I'm writing code in C, or I'm writing code in Haskell, I'm viewing the world in different kinds of ways, and I'm solving the problem in different ways, and I'm susceptible to different kinds of cognitive errors. Some languages enable more of those than others, right? With Rust, I had to do a little bit of work before it gave me the same crappy results that I got with almost no work in C. So, your mileage varies. If we can provide guidance that is reasonably succinct, in other words, something you can pick up a book and learn, then it becomes actionable. It gives us a guide we can use to help write better, and in this case, more secure code. This lets us transfer some of our risk to that guide, right? So I have risk, right? I write some code, it gets used in a nuclear reactor, and now everybody in the world is suing me. And I don't like that, so I need to find somewhere to transfer that risk. Maybe I can say, hey, I followed this process. I took this training, I followed this process. I read Robert Secord's book, I did everything he told me. Okay, and so I try to transfer some risk to that. That's my argument that I took reasonable steps. What about the rest of my risk? Hopefully I can translate that to my insurance company. All right. And there are several different coding guides. There's lots of coding guides. Two that I like to pick on here is the one up at the top, the SEI Cert C Coding Standard. There's one for C++ as well. And the MISRA Secure Coding Standard. And these are fairly commonly used coding standards. The CERT guidance is long, the MISRA guidance is shorter, and you may think, oh, I want the shorter one. Well, keep that thought in your head. Okay? The C coding standard from CERT, one of the things you can do is go out and get Robert Secord's book, Secure Coding in C and C++. I recommend it for a lot of reasons. Learning good ways of writing secure code is one of those. In an undergraduate class, we would trying to make you write secure code. I'd make you all buy a copy of that book, and we would tear through that. Here's the table of contents for the SEI Cert C coding book, and it's long. And you look at it, and there's lots of stuff going on. For example, here in Chapter 10, Input-Output, we have 10:11, avoid Toctau, that's time of change, time of use, race conditions while accessing files, Over here, guarantee that storage for strings has sufficient space for character data and the null terminator. Lots and lots of good stuff in here, but you can see it's, we started out at page 23 and we're down here at page 445 and we're still not done. Okay? In fact, it's gone off the edge of the slide. So lots of stuff in here, but it's good stuff. Strongly recommend, taking at least a look at it. And there's good information in here. Information that you might not necessarily think of. Stuff that you may have been told, like don't call system. And this will explain to you why you don't need to call system. And notice it starts on 340 and goes all the way to 347. Lots of good advice there. All exit handlers must return normally. And then there's stuff that you may be a little surprised by, like do not copy a file object. What? Why not? And so I'll leave that to you to go read it. All right. And now, here's the table of contents from the MISRA guide. We start on page 37 and we go all the way to page 172, and we have good advice in here, and you think to yourself, wow, that looks like I gotta do a lot of reading, and this looks like I don't gotta do as much reading. I'm gonna lean toward the MISRA guidelines. Fine, MISRA looks great. I'll give you that, absolutely. The rules are sufficiently structured that they can be checked automatically, and that's great. LDRA is a way of doing that. You can go and find it here. And that's wonderful. That's super good. Here's an example of one of the MISRA guidelines, Rule 12.3. The comma operator should not be used. What's the comma operator? You've probably not thought about it that much, but you may have used it. Down here, we have a for loop where I initialize a variable and then I initialize a second variable, and for those two initializations to happen, I use a comma. And in fact, I can put commas almost anywhere. Here in my increment, I do two different increments, and I separate them with a comma. The purpose of the comma operator is to chain together several different statements or expressions, with the final one being the value that's actually returned. In this case, we don't care about that, but that's how that works. And MISRA says, don't use it. Okay, just don't use it. That's a reasonable thing, I guess. Why do we not want to use it? Use of the comma operator is detrimental to the readability of code, and the same effect can usually be achieved by other means. So it looks bad. Fine. All right, fine. Here's another one. Rule 21.3. The memory allocation and deallocation functions from standard lib shall not be used. It's a pretty strong statement. What does that mean? That means calloc, malloc, realloc, and free shall not be used, and no macro with one of these names shall be expanded. Wait a minute. I can't use memory allocation? What? Rationale. Use of dynamic memory allocation and deallocation can lead to undefined behavior. For example, memory that was not dynamically allocated is subsequently freed. That's the free before allocate, or double free. A pointer to freed memory is used in any way, and accessing allocated memory before storing a value into it, that's also bad. These are all bad things. Don't do them. Wait a minute. I use these things all the time. So wait, maybe MISRA is too strict. Yeah, it's pretty strict. All right. No dynamic memory. That's a game changer, I think, for a lot of people who would gravitate toward MISRA. MISRA is used a lot in the automotive industry and control systems and so forth, and it makes sense. In those cases, you typically want to have things that have statically allocated memory, right? I get a chunk of memory, and I'm going to compute with that, and I'm not going to have the case of running out of memory or any of that, because I'm not going to be dynamically allocating and freeing memory as I operate, right? Critical control systems, you shouldn't be doing that, right? You're launching a rocket, and while that rocket is going up into space, and it's firing the boosters, and things are gimbling, and there's gyroscopes and controls and all that, it doesn't need to go, I need to allocate some memory, right? That's bad. What if it fails? What do you do then? Do you, just stop running? That's not good. So dynamic memory allocation is not great in some contexts, and miserable just goes ahead and tells you no. Whew. So that's it. We'll talk next time.